Hello, I'm Maz Barami from Wolfram Research. Today will be the 8th session with Andreas Lauschke. He's a senior mathematical programmer who has been using mathematical systems for over 26 years. Today's session will look closer at rarer probabilities and how to simplify its computation by exploiting particular knowledge of the underlying distributions. A modern-day data scientist will be confronted with probability distributions all the time in his statistics work. The integral simplifications will be used also in more general settings than rarer probability. Andreas, handing over to you, looking forward to your 8th session.
Yes, hello everybody. Thank you for the introduction, Mats. Hello everybody, welcome to my session number 8. Today I will be looking closer at rarer probability. I had already introduced it during my last session. I would like to use rarer probability to explain a couple of general features of continuous distributions that you should be familiar with as a data scientist who deals with continuous distributions all the time. I will then apply them directly to rarer probs. And I will split this session into two parts. In the first part, I will discuss the exploitation of knowledge of a particular distribution, which then makes it possible to compute the resulting integrals faster. And here I will in particular focus on the exploitation of symmetry. In the second part, I will discuss some far-reaching consequences of the facts that not all of the continuous distributions have tails, not all of them are unimodal, and not all of them are symmetric. And again, these consequences are generally applicable and they have nothing to do with rarer probability specifically. But there are some characteristics of continuous distributions that you will face all the time when you're dealing with them as a data scientist. All right, so let's jump right into it. We are starting with a reminder on rarer probability and probability. So, as you will remember from the last session, the rarer probability is the probability that the PDF of the distribution in the variable that we're integrating over is less than the PDF of the distribution using the independent variable. And probability implemented in the mathematical system is the integral over bool, that is a binary function, a 0-1 function, of a predicate times that PDF. That's for the continuous case. And for the discrete case, we're using the sum for what is essentially the same, bool times the PDF. And if we think about it intuitively, that also makes sense and is in a very general form provided to us. Bool times PDF clearly means that if the predicate is false, we're not accumulating, and if the predicate is true, then we are accumulating over the PDF. So these are fairly natural, fairly intuitive, and the fact that the kernel provides it to us in this form makes it very flexible, very general, because that way we can also handle some very unwieldy functions. So that means rarer probability in a general form is this integral, right? As we've seen before, it's the integral over this Boolean characteristic function where we have PDF of dist of y is less than PDF of dist of the independent variable. Note that x is blue here, that makes it the independent variable. Y is green here, it's the localized variable over which we're integrating. Yep, then this bool times this PDF. Okay, but that can sometimes be a little bit inefficient. This computes the points of the PDF that are less than some arbitrary value x. And it requires the recalculation of the PDF for every element in this subdomain. And this is oftentimes inefficient. The same thing can be accomplished by calculating the integration limits for the subdomain to obtain all the elements of the subdomain, for example, of a normal distribution outside the range of, for example, -3 to 3, all you need to do is really, figuratively speaking, select from the domain everything that's outside that interval, everything that's not inside -3 to 3. Right? So in particular, symmetry can be exploited in a symmetric distribution, and I will now show you several simplifications. So for the first example, we're using the standard normal distribution again. So let's define it. We need the ndist and we need the PDF, and we need cutoffs for the integration limits. So here I will plot you the standard normal distribution again, and here note that we have several cutoffs, and in this manipulate we can just pick them here with a slider. So that means we are interested in these red regions. They are outside of the domain, the subdomain defined by cutoff, and we are integrating over these segments, and that gives us the rarer probabilities. You remember that the rarer probability is an integral. It is not a point, it is an integral, it is an area, and this is how we are representing this. Okay, so in this particular case, what we're doing is that we're integrating the PDF from -3 to 3. That's the region that is normal. That is the normal region that we're interested in. And we're subtracting it from 1 so that we're getting the rarer prop. And you will remember that it's a requirement for distribution that the integral from -infinity to +infinity is 1. That's one of the 4 requirements that we have for a distribution. So if we are subtracting the region that is normal from everything, then we have everything that is not normal. So this is a very efficient way to compute this, and it also ends up being the fastest way, as I will show you in a moment. And note that these are the values that we are already familiar with from the last session. It's 1 minus the error function of 3 over the square root of 2, or 0,027. These are the same numbers as in the previous session, and this one uses now the error function. And in the last session we had used the complementary error function, but it's not a problem to convert one into the other. That's really the same result, because the complementary error function is 1 minus the error function. Okay, so let's plot it, and again we see the result that we had seen in the last session. This is exactly what we had computed last time, and now we're doing is 1 minus the integral over the PDF. Okay, but note that things are already getting a little bit complicated here for this very simple plot. For a symmetric distribution like the standard normal distribution, we have a right tail and we have a left tail for one number x. And x can be a positive or a negative number, and here we're plotting over positive and negative numbers. So let's say we mean the positive number x equals 3, that would be somewhere here. For example, then we need to integrate from -3 to 3, right? We're giving one positive number, we need to integrate between the negative version of that number and the positive version of that number. But for a negative number, we have to do the same thing. Say we have x equals -4, we need to integrate from -4 to 4. So one number here implies two numbers. Right? A positive number implies its negative counterpart and the positive number, and for a negative number as well. A negative number also gives us two numbers. So the only way to plot this now is to write it as minus the absolute value of x and the absolute value of x in order to make sure this is a negative number and this is a positive number, and you will find this here. We need to do that in order to guarantee that the lower integration limit is the negative version of that number and the upper integration limit is the positive version of that number. That can be a little bit tedious and complicated, but the plots also show us something else. The plots are symmetric around 0. So if we look at this, then we see that we have, in both cases, in the PDF and in the rarer probabilities function, we have a left part and a right part, and they have the same area. They have the same size. And we can use this. We can speed up the computation if we are computing just 1/2 and then multiplying that number with 2. That gives us the entire area. And the symmetry, we can also show mathematically. As you will probably remember, symmetry over the x-axis is defined that f of x equals f of minus x, right? So if we take the positive number or the negative number, f of that number is the same, f of x, x being positive, and equals f of minus x. So this is exactly what I'm doing here. I replace t with minus t, and we see that we get the same results. The functions are clearly symmetric. The PDF is symmetric, and the rarer prop is symmetric. So we can use this in the future. And it's even true in the complex case. We didn't even need to refine in this one. This is generally true for reals and for complexes. Okay, so given that integration can be very time consuming, and this is true for definite integrals and indefinite integrals, both for symbolic as well as numeric, right? We have 4 cases here, 2 by 2 of these cases. We can now split this up in the middle and perform only a one-sided integration and then multiply the result with 2. So let's do that here. We are integrating in the first case only from -3 to 0 and multiply with 2. In the second case, we're going from 0 to 3 and multiply with 2. Same thing. You see we get the same result. So we have really sped up the computation by 2. And you see that we're getting the same results. And this particular version is my favorite version because we also avoid the indefinite integrals, right? We're integrating from 0 to 3 or -3 to 0. No infinities here, and that makes it particularly efficient and particularly fast to compute. So in other words, the way I can describe this is that rarer prop is everything except for the stuff that is not rare. Right? It may sound trivial, but this is the representation of exactly this PDF here that we have. This clearly means we want everything minus the part that is normal. So what we get then is the part that is not normal, that is the rarer probabilities. That is 100%. Remember, PDF must have an integral from -infinity to infinity, that's exactly 1, minus the left or right half of the normal. And that is easier to compute because we don't need plus minus infinity. Okay, so if we're now using this in a timing comparison, we see that the version is relatively fast. I have for the first one here 67 milliseconds. For the second we have 26 milliseconds, and we can even get it faster when we use nintegrate. Nintegrate performs only numeric integration, not symbolic integration, and then we can really get it down to, what do we have here, 9 milliseconds and 6 milliseconds. Okay, significantly faster. It's like a blink of an eye, and we have computed the correct values this way. So in the second example, I'll show you an equivalent computation. We're adding 2 parts integrated separately from -infinity to the lower limit plus the upper limit to infinity. And this now involves 2 integrals instead of 1, and both integrals are indefinite integrals, right? Not as good, definitely not as good, but it gives us again the correct value from -infinity to -3, and then we're adding the integral from 3 to infinity. Gives us the same result. Again, our numbers that we're already familiar with. And if we plot it, we get the same curve again for this rarer probability. But here we have the same problems as we had before. We need absolute value to simplify it in order to be able to plot it. And we know that the left integration must have the same value as the right integration. So we can really simplify it, and instead of making it one integral, now instead of making it 2 integrals, we make it 1 integral and multiply with 2. So here again we get the same values. In one case we go from -infinity to -3, in the other we go from 3 to infinity. Okay, but that now takes longer. Let's do the timing here, and we see that we now have 834 milliseconds here, and we have 517 milliseconds here. And the nintegrate versions are about the same speed as the first ones that we had, a little bit longer, right? So here we have 10 milliseconds, and here we have 7 milliseconds. Okay, again, nintegrate wins, but still the entire situation is still not as fast as in the first version. And it also shows us here nintegrate is pretty smart internally. The numeric version takes about the same time as in the first example, and that's because there's a lot of algorithmic smartness under the hood in nintegrate, so that it's relatively easy for that function to deal with the two infinities at the right and at the left end. But in general, still try to avoid infinities in these indefinite integrals, although for an integrate that's not a problem. And I'll show you the third way to do this. And like in rarer probabilities, make the integrand the product of bool of the predicate times the PDF. And this would now exclude the inner interval in the predicate. So let's look at this. The area between -3 and 3 is what we're interested in, so we leave it out, right? We are negating this with the exclamation mark. So our predicate bool now only provides a support for integrate when it's outside of this integral of this interval -3 to 3, then times the PDF. Okay, and if we compute this, it's taking longer, but we're getting the same results, and we're plotting it. Again, this will take longer, and we have the same problems as above. We needed apps for a simple plot, and we don't exploit the symmetry. And here we have both plus and minus infinity in one integral. Really not efficient. So if we do the timing results here, then we see we get the same numbers, but it takes significantly longer. The nintegrate versions are again much faster than the versions that take the symbolic computation, right? Integrate is the symbolic function, nintegrate is the numeric function. And we see that they're faster when we're splitting up the subdomains. Here we're going from 0 to 3 and then excluding it. Here we're going from -3 to 0 and excluding it. We do the same thing in the symbolic versions, that is these two integrals, but we clearly see that the symbolic versions take longer. Those are the first 3 rows here. The numeric versions are significantly faster, and the fastest versions are when we are splitting it up into 2 subdomains and then simply multiply with 2. And also in the symbolic version, we are seeing that we are getting faster results by splitting it up and multiplying with 2, right? Okay. And now even the nintegrate versions take a bit longer. Yes, it's because the integrand bool of predicate times PDF is more involved. All right, and now let's look at ground truth. After all, we just were trying to recreate rarer probability itself, and we see we get the same number, and we need half a second for this, 534 milliseconds. Okay, so to get deeper into those timing results, I'd now like to see a competition with 1,000 random variates from a standard normal distribution. So let's create them. We can use the function random variate for that. We need to give it the distribution and then the number of samples that we want. We store it in RV, and now let's do a timing result. And when we do it this way, we see clearly that we're getting the fastest result when we are splitting up the domain. And we also see that we are getting the fastest result when we use what I introduced as version 1. 1 times 2 times the integral that is only one-sided. So we see for 1,000 random samples from this normal distribution, the fastest result is the first one, and the second one is not too bad, but the longest one, the one that takes the largest amount of time, is the numerical integration over bool times the PDF. And if we wanted to do it with rarer probabilities directly, it takes so long that I had to go down from 1,000 samples to something like 10, because otherwise we'd be sitting here until the cows come home. And with 10 samples, it takes about as long as the slowest version above. So that will also take some 10 or 11 seconds here. Yeah, 11 seconds. So it's about the same result. So in other words, this version is about 100 times slower, right? We use 1,000 samples above, and here we're using 10. It's the same amount of time, 11.6 seconds. So rarer probability is about 100 times slower than when we are creating these integrals ourselves, exploiting the symmetry here. Okay, so we have a clear winner. Nothing beats the version that I would describe as numerically integrate from 0 to threshold, double it, and then subtract from 1. Now keep in mind, the center doesn't have to be 0. I'm using 0 here, but the standard normal distribution and also the non-standard normal distribution always are symmetric. So the center doesn't have to be 0, but it is symmetric, and we can exploit that fact in order to speed everything up. So we could perhaps further improve the speed result by using C compilation, and I haven't tested this. And even more for massively parallel applications, we can use CUDA, and we can also use, of course, other distributions for this. And simulations are a great example of an application that uses samples that were generated and evaluated massively in parallel. So CUDA would be another version to speed this up by magnitudes, but for that we really would need a massively parallel application for this. Everything I've shown you so far was not parallelized. Everything here was single-threaded. So there are additional ways to speed this further up. I believe with C compilation we can make it even faster. And when we need parallel samples, we would use CUDA. Okay, however, the version that RarerProbability uses with bool of the predicate times the PDF is more flexible and can be used for more general problems to select the wanted events. But it's definitely much slower due to its ability to handle much more general problems. Okay, and with that brings me to the second part of today's session. I want to specifically emphasize that not all distributions are symmetric, not all of them have tails, and not all of them are unimodal. So keep in mind, rarer probabilities works on both sides, and that includes smaller parts of non-symmetric distributions. And this is oftentimes overseen because sometimes we just look at one side, usually the right side. We're typically using the right tail as the foundation for our reasoning, and then quite often forget the left part of it. And remember when in the last session I said that the curves of the rarer probability would look different for different distributions or parameter. I will illustrate that now in the following examples. And in the next example I will use the Fréchet distribution. So for this example, let's cut off the right tail at 3, and I want to emphasize again that this is a point and not an integral, and not a probability, and not an area under a curve, right? When we're talking about probabilities, those three things are the same. Every probability is an integral, and that's an area under the curve. But here we're talking a point. We are simply looking up 3 in the PDF. So this is a point. This is a value on this curve here at this particular point. We're not talking probabilities yet. We're just looking up a point on the PDF. And we want the rarer probability, but everywhere it occurs, not just on one tail. So here, if we are looking it up on both tails, and at this point, keep in mind, this is now a probability, and it's also an integral, and it's also an area. It's not a point. So this number now represents a two-dimensional area. It's an area under a curve. It's a probability. It's an integral. And let's plot it, and I've already done this because it takes several minutes to compute, so I've already done this. And we now want to solve for the other point. We already know that 3 is the right-tailed number that we're interested in, but we don't know yet what the left-tailed number is. So let's simply solve for it, right? We know the formula for it. It's the PDF of the distribution at point x, which we don't know yet, and we set it equal to the number that we already know. The PDF of dist at 3 we have already computed. So we know that 3 is one solution, and the other one we didn't know. We've computed it now. It's the value where the same PDF value is attained, and we're getting the result back as a root object. And I think it was in version 10, maybe it was in 9, that this display was changed in the front end. You now get the root object when you hover over it. You can see what the root object is, but in the front it is displayed as the numeric value of it with a circled square root symbol in front of it. I think that's a great solution to the fact that previously many people found it confusing to just see those root objects there, and then they had to convert them to a numeric value on their own. So I think we can now clearly see what the numeric value is, but we're not losing the information on the root object. Okay, so let's now get both tails RarerProbability, and we're now using these two integration limits. We're going from -infinity to the lower limit, and we're going from the upper limit to infinity. Right? This is again now two separate integrals, and we cannot exploit symmetry here because the Fréchet distribution is not symmetric. So we have to do it as two separate integrals now. And here is the number. Take a note of it. It's 0.0372426. We need that number in a moment. Okay, and here we see that the RarerProb equals the both tails prop that we had just computed. When we set them, when we ask if they're the same, we're getting true. All right, that's great. And now let's plot this situation. And what do we see? We see clearly the right side above 3, but it's easy to miss that we have a very small itty-bitty patch of red here on the left side from -infinity to 0.522. This is exactly the lower limit that we had just computed, and it's very easy to forget. It's very easy to miss. So keep in mind, just because we don't have a symmetric distribution doesn't change the fact that we still have a left tail. And let's not forget the left tail here. This is a small area here that we have to include in our considerations. So values less than 0.522 would be considered an outlier, right? Remember, we're using rarer probabilities in find anomalies in order to detect whether or not something is abnormal, whether or not something is an outlier. And that is because the integration begins at -infinity, right? So that's always where our outlier consideration begins, and it goes up all the way to 0.522. It is hard to believe when looking at the shape, but never let the shapes fool you, right? Very clear we have rarer probabilities here on the left. There's clearly red, and red means rarer probability. And in general, with extreme value problems like we have in volatility in financial trading, or we have in insurance problems, you will generally want only one tail. It's usually the right one, as insurance problems generally look at the loss of a positive cost of the event. And when talking billions of dollars, and that is the case in many insurance problems, this integral, this is the number that corresponds to that. That can be a huge amount of money. And also consider the potential for lawsuits over lack of contractual clarity about one-sidedness versus two-sidedness. Right? It may not look like a big deal, but if you multiply this number with billions of dollars, then you're getting big numbers, right? You're getting seriously big numbers. Let's just not forget this. This is the rarer probability for this lower limit of 0.522. Okay, yes, and keep in mind that there can be huge lawsuits over lack of contractual clarity. Are people talking about really both sides, or is it assumed that it has to be one side because it's a large tail distribution, a large right tail that we have in this case? So definitely make sure, if you are involved in contract negotiations, that this is required. We have two tails even in non-symmetric distributions. It reminds me about the lawsuit about the Twin Towers in Manhattan. Was it one attack or was it two attacks, right? And was it one building or was it two buildings? So it was clear that one of the buildings was insured, but it was not clear whether both Twin Towers were insured separately. And there were several lawsuits over this, and the courts actually ended up not being clear. There were some juries that decided it was two separate attacks because it was two planes hitting the two towers, and there were some juries that decided it was only one attack because the two planes coming into the Twin Towers were a coordinated attack. So definitely I'm pointing out to you that definitely make clear, if it's ever important in contracts, are we talking one-sidedness or two-sidedness here? Okay, so somewhat summarizing, people often forget that rarer probabilities and find anomalies are concepts that do not require symmetry, right? Tails can have different shapes, and here we have that. And in fact, rarer prob can include areas, and here that means integrals, that are not on tails, but in the middle. And this is also, I think, something that can be overseen very easily. And I'll use a bimodal distribution that I have constructed simply from two normal distributions. Let's look at this. All I've done is taking a normal distribution centered at -3 and another normal distribution centered at 3, added them together and divided by 2. Well, this gives us a bimodal distribution. It gives us the sum of two normal distributions, and that makes it bimodal. And we define the distribution for this. I've shown you last time we just used probability distribution over that PDF, and now we have properly defined it as a probability distribution because a function is not immediately a distribution, but this is the way to declare that in the Mathematica system. Now let's plot them, and we can clearly see that as the sum of two normal distributions that have equal distance from 0, we are getting a bimodal distribution. To be proper, we now have to use the 4 checks to see if it's really a distribution. So the integral from -infinity to infinity has to be 1. It has to be larger, equal to 0 at all times. And that looks good, and we'll waive the check if the function is integrable and real. Well, as the sum of two normal distributions, it's definitely integrable and it's definitely real. So that completes the 4 checks we have to use on distributions. So let's compute a rarer probability for 5. I'm just picking the number 5 here. Okay, we're getting a number. And what's the value of that PDF at the number 5? Okay, that's another number that I will be using in a moment. And we store it away in lim value. Okay, and now let's plot the whole thing. And you will see that there is a red area in the middle. And there's no tail here, right? We have a right tail, and there's a rarer probability. We have a left tail, and there is a rarer prob. But we also have rarer prob here in the middle. And it's not a tail by definition. If it's in the middle, then it cannot be a tail. So keep that in mind. It's quite important to emphasize that, because many people are only looking for rarer probs in the tails. And to avoid misunderstandings, I emphasize that when it says in the help browser, it computes the probability for distribution dist to generate a sample that is a lower PDF than example. That really means that has a lower PDF than example has, right? Because example has a PDF. It doesn't mean than example is. It is has, not is. So lower refers to the y-axis, not the x-axis. It's not that with lower we mean everything less than the cutoff. We had picked a cutoff of 5, so it's not everything to the left of it. It is everything that is below the value at the cutoff point, right? Everything that is now in red under this cutoff level, which is lim value, right? So we could just as well have taken any other of the 4 points that attain the same value. It's not that I need to define this level with the right 5 here. I could have taken the left limit, that would be -5, or I could have taken these 2 points here more in the middle. And to show that, let's compute the other 2, that's the 2 in the middle. So I'm using find root on this because it's a rather involved function that we're trying to solve here in the middle. So I use find root for that. And I try to get 100 decimals for that, just to be precise. And now let's check all 4, right? We should get the same number for lim value. And we can then make an easy comparison here. So we should get 4 rows where the columns 2 and 3 are the same, right? We see that these are the same. I'm sorry, columns 3 and 4. We see that they are the same. This column is always lim value, and this is the computed value. That's PDF of dist at the numbers that I'm checking, and we see they are the same. Columns 3 and 4 are identical, including for those 2 numbers here in the middle. Okay, so we could have taken any one of these 4. It's not that it's only lim value at 5. Okay, but we can also do more. How about try model? And we don't need to have the center of it at 0. I do, right? I still keep it at 0, and now I have to go equal steps in both directions. So I have a -5 here, and I have a +5 here, and now I have to divide the sum by 3. How about try model? I have to define the distribution again because I'm gonna need it in a moment. Let's plot it, and we see that we now have 3 tops and we have 2 local minima here somewhat in the middle. Okay, so let's check if it's a distribution. Yes, it is. And now let's compute the rarer probability at 7. I'll just pick a right upper cutoff value here. That is a 7 that I'm just picking somewhat arbitrarily. We get a number 0.04. Let's also compute the corresponding lim value. And again, let's plot it. And now we see that we have 2 subdomains in the middle, right? We have a right tail, we have a left tail, and we have 2 subdomains where we have a rarer probability that is defined by this cutoff. Okay. Again, we see clearly that we're talking about areas here. The red areas are not points, but areas. So that's a probability, and it's an integral, and that's exactly what we need for rarer probability. So here, let's do the same thing. Let's try to solve the other cutoff. So we need 4 of these. We need 2 for the left region, and we need 2 for the right region, but they're symmetric. So we can also say here the inner ones and the outer ones. So again, I use find root. I'm trying to get 100 decimals, and we see we have these 2 numbers here, 2.05 and 2.925. And now let's check all 6 of them, right? You see it's 6. It's 1 here for the lower cutoff, 1 for the upper cutoff, and we have 4 in the middle. And this computation now will take a while, but eventually we see that columns 3 and 4 are again identical for all 6 points that we are testing this on. So after a couple of seconds we should get our table, and we can clearly see that we have the same numbers in columns 3 and 4. So with this I want to emphasize that you should please note that rarer probability and find anomalies don't inherently rely on tails or symmetry. But if the distribution is symmetric, computations can be significantly sped up. In fact, roughly by a factor of 2 if you're using 2 times the integral over a symmetric subdomain. That was part 1 of this session. And here we have the results. We see that columns 3 and 4 are identical for all these 6 points, including these 4 that are in the middle. Okay, and I think this gives us also a way to test find anomalies, coming back to what we had last time. So let's generate some 10,000 random variates from this particular distribution, and now let's use a histogram on the results of find anomalies, and you see that we have generated these random variates based off dist, and dist was defined as we have seen here with those 3 maximums, and we can clearly see this when we are now sampling this and using find anomalies in order to find where we can even have any samples that are possible in these subdomains. So I'm using bin width of 100 in the histogram, and we can clearly see that we here have these 4 areas where we can have samples in that histogram. Okay, great. So that brings me at the end of my session. Mats, do we have any questions?